The next mirror type we're looking at is a convex mirror. It caves out, it bends away from you.
You mean concave?
Yes, I mean concave. I'm sorry. I don't even know what I said then. I must have said convex.
Yeah.
Concave bends away from us. With a concave mirror, as you look at yourself right now, what can you tell me about your image?
Upside down. Upside down.
You're smaller, you're upside down.
I'm better looking this way.
You like it much better than the normal mirror? Convex mirrors. Now it turns out, if you get really, really close to this mirror, your image will flip over and you'll be right side up. The image will be right side up and bigger. I'll pass it around so you can look at it. So what type of image we get with the concave mirror depends upon how far away the object is. If as you get closer and closer and closer to the mirror, your image will be upside down to begin with, and it will get bigger and bigger and bigger as you get closer and closer. Once you reach the focal point of this mirror, the image will end up flipping over and become upright and bigger. Concave mirrors are used in shaving mirrors or cosmetic mirrors. That way it magnifies the image so you can see things better, which is always a little disturbing to me.
Now the concave, when you get to that point where, I'm just thinking Death Star again, where all the light gets...
It's focusing.
That's where you're going to see yourself flip over upright.
At that focal point, you won't see it. At that exact position, all you'll see is a big blur. It's once you pass that position that you'll see yourself upright.
But a Death Star won't actually work because you'd actually need a lens over there to stop all the light rays from going through
It's
each
possible,
other.
we just haven't found
It says it's light.
We're not too worried about it at this point in time. So. Concave mirrors are also used in telescopes. They help focus the light down. They're used in conjunction with lenses and other mirrors. So hold it out from you, pull it in, you can see that the image changes.
I'm sure the focal point is
Farther away than what you would normally stand from it. Exactly. Similarly to what we did with the convex mirror, if we draw light rays coming in from far away, we know they reflect off at the same angle they come in at. If I draw a couple of these, turns out with the concave mirror, the reflected light rays would actually converge together, come together. This point where they actually cross is called the focal point. It is a real focal point. Light really passes there. They pass and converge at that point. Mathematically, we use a positive value for our focal point, for our focal length, when we use our equations. Okay? The equations are the same. The 1 over s plus 1 over s prime still equals 1 over f. The magnification is still negative s prime over s. That's all still valid. So one thing that's different for concave versus convex is that our focal point, our focal length now is positive. So as I said a minute ago, what type of image we get is entirely dependent on where the object is. So I'm going to draw a reference line again. And I'm going to put our object out here somewhere. So fairly far away from the mirror. And again, we're going to draw a couple of light rays to represent what's happening from the light leaving this object. We're going to draw one straight to the mirror. When it reflects, it will reflect off and pass through the focal point. So that's one light ray. We need at least two to estimate where the image will be. Our second light ray, I'm going to draw one through the focal point. It will reflect off so that it's horizontal. Since I drew the light rays leaving the tip of the arrow, where they actually cross is the tip of the arrow. This is our image. This is our object. The object distance is the distance from the object straight over to the mirror. Image distance is from the image straight over to the mirror. Okay? This image is real. It's really there. Those light rays actually physically cross. They come together, they converge together, they cross. We have an image there. Which means we could actually take an actual physical screen, movie screen of some sort, place it right there, and we would see this image on the screen. Okay? Since it's a real image, if you were doing a mathematical problem to solve for S prime, you would need to come up with a positive answer for S prime. Our image is inverted, which means mathematically we would need to come up with a magnification that's negative. Now, as long as your object distance is bigger than the radius of curvature, then your image is going to be smaller than the object. Looks a little bit smaller here. Kind of hard to tell when we're freehanding things. As we bring the object in closer and closer and closer, that image is going to get bigger and bigger and bigger. Okay? As we get closer and closer and closer, the image gets bigger and bigger and bigger. If S is less than R, but bigger than F, well, actually, your image will be bigger. So the radius of curvature is twice the focal point, so our radius is out here somewhere. As long as our object's between here and here, the image will be smaller. At R, if your object was physically at the location of R, the image would be exactly the same size as the object. But as you come in, if you bring the object closer and closer and closer, the image continues to get bigger and bigger and bigger. It's bigger than 1 once you get, the magnification is bigger than 1 once you get past the radius of curvature. Now this is not the only type of image we can get. We only get a real inverted image if our object distance is bigger than the focal point. Okay? If we bring our object in closer to the mirror than the focal point, so there's our object. When we draw our light rays, if I draw the one straight over, it's going to reflect down through the focal point. If I draw the one along the line of the focal point, it will reflect off the mirror horizontal. Those reflected light rays diverge. They're not going to cross. That's when we project them backwards. Our brains see them as if they converge back here. Again, since I drew the light rays leaving the tip of the arrow right here where they appear to cross, is the tip of the arrow. We get a virtual image here, meaning S prime mathematically would need to come out to be negative. It's upright. The magnification is positive. The image is going to be bigger than the object. Now this is, as long as the object distance S is smaller than the focal length F. This is the result we will get. So with the concave mirror we can get both real and virtual images depending upon where the object happens to be placed. So as Ben was asking, we have a cosmetic mirror or a shaving mirror. If you're looking in one of those, the focal length of the mirror is always bigger than what you would traditionally hold it from your face to look at. So that puts you, the object, inside the focal point, which creates an image that's upright and bigger and disturbing. I find it a little disconcerting to look at those. Questions so far? If your object is placed at the focal point, 1 over s plus 1 over s prime equals 1 over f. If s is equal to f, we get infinity for s prime. It doesn't form an image. It just looks like a big blurry mess. You don't get a nice pretty image at all. So outside of the focal length, you're going to get a real inverted image. Inside the focal length, you're going to get a virtual upright image.
So on the first one, s being the distance from the object to the mirror, if that's bigger than the radius of your mirror, you're going to be smaller.
Correct.
The image will be smaller than you.
Correct.
Does it matter if S equals R?
No, s can equal r. What that will mean, if s equals r, that means your magnification will be 1. So your image will be the same size as your object.
So in a shaving, no, I guess you want more magnification.
Yeah, the shaving mirror, it's generally to magnify you somewhat, so you are inside the focal point.
Okay.
Plus, if you were at r, you'd still be upside down, which wouldn't be very helpful if you're trying to shave.
If you stared at it long enough, your brain might flip it.
It's true. They have done, I have heard of studies where they gave people glasses that inverted all the images, and they wore them for a couple days. A couple days later, everything was normal.
Well, it's because our iris flips it in our brain.
Yeah, and our brain will make sense out of it.
Yeah.
Our brain doesn't like things to not make sense. So it made it flip the images back, so everything was normal again. But then when they took the glasses off, everything was upside down for a couple days.
Well, it's like when you start speaking another language, or you go to another country, you speak another language, you can start thinking in that language instead of thinking in, like English.
Certainly. Certainly. Our brains are amazing. What?
My brain doesn't do that for me.
It's not speaking physics yet.
Your eye is similar to a convex mirror?
Lenses.
The lens in your eye is similar to, yes, a concave mirror in terms of what it does. It's shaped convex, but the images it produces are comparable to a concave. We'll look at it.
It's concave convex, isn't it, sort of?
The convex mirror, convex lens behaves similar to a concave mirror, and then a concave lens behaves similar to a convex mirror. We'll talk about lenses.